Hello all. So today we will be talking about coupled mode theory. Right. So to begin with, first let us recap what are modes. So modes in a waveguide are the solutions that propagate in the waveguide. So the propagating modes are called guided modes. The ones that do not propagate are radiation modes. So these are basically the solutions of the wave equation uh, if we, inside a waveguide with the boundary necessary boundary conditions. So these solutions have certain properties. One thing is that they are orthogonal. So in an ideal waveguide, the modes are orthogonal. What that means is the intensity in one mode would not spontaneously transfer to the power transfer won't happen between different modes. So they are independent of each other. But in case we have a perturbation in the waveguide, so say this is my waveguide. This is the film refractive index, this is the substrate refractive index and cladding refractive index. If there is a slight change in the refractive index in this region, say, okay, then that acts like a perturbation. Now the modes are no longer orthogonal, and the power transfer can happen between the modes. So this is called as coupling. So perturbations can be used for mode coupling. So that is the whole premise of this coupled mode theory discussion. So we will have a waveguide which will have its certain orthogonal set of modes that act as a basis. So any solution for the waveguide can be written as a sum of these modes. So then we introduce this perturbation, and because of the perturbation, the intensities are exchanged between the modes. So if the intensity of mode 1 was A1, intensity of mode 2 was A2, then now after the perturbation, the intensities of both the modes get shuffled. So that is the coupling. So right. So first of all, we need to know what are the mode solutions for the waveguide in the unperturbed situation. So for the unperturbed case, let me write down the modes. So in the unperturbed case, a waveguide can support finite number of guided modes and infinite number of radiation modes. So this is from the fact that the guided modes are finite, discrete. So we will have certain number of modes corresponding to beta 1, beta 2, like that. But the radiation modes will have a range of betas in the region smaller than k naught nf and larger than, if ns is larger than nc, then we'll have k naught ns. So since it's a continuous range, there will be infinite number of radiation modes. Okay. So yeah, so all these solutions are basically the solutions of this particular wave equation. The wave equation is given by, for a, say, if I have this as my x coordinate, so the boundaries are in the x region, the propagation is in the z region, and since it's a, we will assume it to be a TE polarization of light that is incident. Then this is the y, and my electric field will be along the y direction. So the wave equation will be del square Ey of x comma z comma t. So the mode profile will be in the x coordinate, z coordinate because it is periodic with respect to z and also periodic with respect to t, because these are the this is the propagation direction and this is time. Will be equal to permittivity times permeability times del square Ey over dou t square x comma z comma t. So this is my wave equation. So we find out all the mode solutions for this wave equation, and then we use the perturbation approach to find the mode solutions for the perturbed waveguide. So we have already done this before, finding the mode solutions for a slab waveguide. So they are given, they are of the form E of I of x comma z comma t is equal to half of ai, so these are the amplitudes, times E of yi of x, so this is the mode profile, times e power minus j beta z minus omega t. So this is the variation, sinusoidal variation. So it is oscillating in the z coordinate and also in the time coordinate, and plus obviously the complex conjugate. So the solutions look of this type. So that's why we have put a half here. So because we will have another half ai as the complex conjugate, right? Here I'll just write down ai is amplitude of mode I EYI of x is normalized amplitude distribution or the mode profile of mode I. So yeah, so the thing to understand is instead of writing the electric field as just the real component, we are writing it in the complex notation. And since we are using the complex notation, we have to add the complex conjugate also, and that's why we have put the half the amplitude in the real in one form of the electric field and half as the complex conjugate. So this is how my wave equation will look for a normal wave. Now for an unperturbed system. So now how do I introduce a certain perturbation? So say if I just have a perturbation like this, how do I include the perturbation in this scenario? For that, introducing perturbation. So the perturbation is in the geometry of the waveguide, right? So what is actually changing is the dielectric constant. So the geometry is changing, that means that the refractive index is changing. Refractive index is changing means epsilon is changing. And how do I include this epsilon? So initially if I had epsilon, uh, permittivity as epsilon, it would become epsilon plus delta epsilon, right? So how do I include this epsilon? So the thing to note here is this epsilon shows itself as uh, a polarization. So if I write my displacement is epsilon times E. That is nothing but epsilon naught times E. So this is just the vacuum permittivity plus the polarization, and this is coming from the material, right? So if I have an epsilon plus delta epsilon case, then what will happen to my D? D will become epsilon E plus some perturbation in the polarization, right? So this is like P pert is nothing but delta epsilon times E, right? So now how will my wave equation look like? So the wave equation will become, sorry, so for the perturbed case the wave equation becomes again del square Ey, there is no change in Ey, mu epsilon, epsilon becomes epsilon plus delta epsilon. So I'll just write the first epsilon term, del square Ey upon dou t square. Now the delta epsilon term, I can write it as plus mu delta epsilon times Ey is nothing but P pert, dou square P pert upon dou t square, correct? So this is my new perturbed wave equation. So this brings us to think about the approach that we can use to solve such an equation. So the approach that we use is the perturbation theory approach. So first what we do is we find eigenmodes of unperturbed system. And then we express our solution to perturbed wave equation in terms of superposition of these eigenmodes Now once we have expressed it as in terms of superposition of eigenmodes, we just substitute it back in the equation to find the solution. Sorry. So let us do it. So we already know how the solutions of this part look like. So the first point is done. This is how the solutions of the first part looks like. So let me just write the most general solution. The most general solution would look like a superposition of the eigenmodes. So let me do that. E of x comma z comma t will be, so superposition means I'll write the summation, I'll take the half outside the summation, half summation over all the modes ai of z, then the mode profile along the x direction times the oscillating term, oscillations in the z and the time variable plus the complex conjugate. So if you notice here, these are all the forward propagating waves. But in general, in a waveguide, I can have modes that are propagating in the z direction and also modes that are backward propagating in the minus z direction. Right? So I should also add, so that this is actually the most general solution, I should also add the modes that propagate in the reverse direction. Summation over ai of z. Just to differentiate these two amplitudes, I'll put a plus here and a minus here. In general, these two amplitudes can be different. So the amplitude of the forward propagating wave can be different from the amplitude of the backward propagating wave, even though the betas are identical. Or even though the mode profiles are identical, it can be different. So yeah. So since this is backward propagating, I'll write here beta iz plus omega t and the corresponding complex conjugate term. Now there is one more thing that we are missing here, and that is the radiating modes. So we need in a general summation of all the modes, we need to include the sum of all the radiating modes also. So now since the radiating modes are continuous, so there are not discrete number of radiating modes, there are infinite number of continuously varying radiating modes. So for those, we instead of writing a summation, we should write the integration. So the amplitude will depend on the beta value. So the beta value changes between k naught ns and k naught nf that we just discussed. Amplitude will depend on the beta value and also on the z value, and then the mode profile will depend on the beta and the x coordinate, and then there will be some propagating term to it also. So this term corresponds to the radiating mode term. However, since these modes are radiating, these amplitudes will die down fast as z increases. So this is just to understand how we should approach the problem. So we have the wave equation, the perturbed form. We have the general solution. Now we need to substitute this solution into the wave equation and try to solve for different amplitudes and mode profiles and everything. So that is a very complicated algebra that we need to do. What I will do here is I'll write down what all assumptions that we made to simplify the algebra, and then I'll write down the final equation. So that way we don't really need to go through all the algebra. All that matters is to understand the final equation. So we understood what is that we are doing. Let us see what we get by doing it. So what we are supposed to do is substitute. So if I call this, we need to substitute the solution in the wave equation. So if I call this as, say, equation 2, so this is my solution. Substitute 2 in 1. If we substitute 2 in 1, and if we assume certain things, so we have to assume, we have to ignore higher order terms. Cancel out certain terms based on the wave equation. So most of the terms will actually, so if you look at these mode profiles, they all satisfy the wave equation in the unperturbed form, right? So those terms will get cancelled out. And next what we do is we multiply the equation that we get after doing all this by multiply by ej of x. So for some particular mode, so that I get the equation for a particular mode. So what I mean by this is, so for any orthonormal mode, it is true that minus infinity to plus infinity ei of x times ej of x dx is equal to some constant times the Kronecker delta function, and the constant is given by 2 omega mu over beta I. Okay, so what that means is the two modes of a waveguide without a perturbation. Okay, so this is talking about a waveguide without a perturbation. We have certain mode solutions. These mode solutions are orthonormal, which means that their product will the integration over all Aij will give us values only at particular chronicle deltas where I equal to j. So now if I multiply whatever equation I get with Ej of x, I will be left with only terms corresponding to the mode j. So finally the equation that we get is multiply by Ej and integrate. Okay. Integrate over x from minus infinity to plus infinity. Then I'll be left with only the mode j terms. So finally I'll get a relation for the amplitudes of mode j. So a relationship between the perturbation term and a change in the amplitudes of mode j. So I'll write down the relation. So that will be dou aj minus over dou z, okay, e power j beta jz plus omega t. So this is the backward propagating wave. So the change in amplitude of the backward propagating wave minus dou ag plus dou z plus e power minus j beta j z minus omega t plus the corresponding complex conjugate terms is equal to minus j by j is this complex number j by 2 omega dou square by dou t square minus infinity to plus infinity p part over x ej of x dx. So just to recap, what we have done here is we basically had the perturbed wave equation. We substituted the general form of the solution in the equation, and then we ignored the higher order terms, cancelled a few terms based on, because del square Ey minus mu epsilon dou square Ey by dou t square will be 0 for a lot of these terms. Okay, we cancelled all those terms, and the only terms that were left were the dou a by dou z terms and the differentials with respect to this. Okay, right. So after all that simplifications, what we had left is the perturbation term. So we don't know about what is the perturbation till now. We have not assumed any particular form of the perturbation. So the perturbation term is left, and the rest of the terms are just the change in the magnitude of the forward propagating wave and the backward propagating wave with respect to z, and the oscillating term with it. Right. So now to go ahead, we need to know what is the perturbation. So from here, what we notice first is one point to note here is that the change in the amplitude of the forward and backward propagating wave depends on the overlap of the perturbation with the mode field amplitude. So the mode profile, if my mode profile, see, if my waveguide is like this, say, however, the refractive index distribution is such that, so say it's some gradient index kind of waveguide, and the refractive index distribution is such that the mode is lying like this, like most of the intensity is in this region. And then if I have a certain small perturbation here, that is not going to affect the mode much. However, if the perturbation is large and if my mode is strongly overlapping with the perturbation, then the change in the amplitude of this mode coupling to some other mode, say like this, some other mode will be higher. So the change in the mode amplitude of this mode will be higher when uh, when the perturbation has an overlap with the mode. So that is the idea. Okay, so now we have to go and look for particular perturbation values. Right, just a minute, I'll take the ruled format. Right. So different types of perturbation are studied in different under different topics. So there are certain perturbations on the waveguide that can cause the modes to couple. So the thing is, either modes with identical beta can couple or modes with non-identical beta can couple. When the beta are not identical, so coupling between such modes of different beta are called non-degenerate coupling between modes. Non-degenerate coupling means beta is not identical. So beta 1 and beta 2, if we are trying to couple these two betas, if they are not identical, if these two modes are not identical, then we call it non-degenerate coupling. So we study that separately and the degenerate coupling separately, because the kind of assumptions that we can make while writing the equations for non-degenerate coupling are different from the degenerate coupling case. So one such example is coupling due to a dielectric perturbation. So say I have a single mode waveguide, okay? This is N1 and it is symmetric. So on both sides I have N2 and N2. And then say I introduce a perturbation in the waveguide. So it was a single mode waveguide, only one mode. Now because of the perturbation, there will be some reflected energy. So now there will be two modes. One mode that propagates in the forward direction and one that is propagating in the backward direction. So just to, so this is my x-axis, this is the z. So the light was initially propagating only in the positive z direction. Now there will be backscattering also. So this point here is z equal to minus a, and this is z equal to plus a. So there is total 2a of perturbation, z equal to 2a length of perturbation. And say if this height is h, this height is h over 10. So yeah, so that is how the geometry has been altered. And now we have to find the new mode solutions. So after z equal to plus a, at z equal to plus a, what will be the backscattered backscattered mode, the amplitude of the mode that is propagating in the backward direction and the amplitude that is propagating straight ahead. Okay, so first, like we saw earlier, we should first write down all the mode solution for the single mode case. So since this is a symmetric waveguide, we already know how the modes look like. And they have also told us that this is a single mode. So the eigenmode will look like Ey is equal to C So first in this region, e power minus, so that will be a radiating mode, x minus h by 2. So I am taking x equal to 0 at this point, center of the waveguide. Fine. So this will be for all x greater than or equal to h by 2. So that's why we are doing x minus h by 2, because it should start radiating from this point onwards. Similarly, in the center we will have a oscillating part. So that will be like a cos term, because my x equal to 0 is in the center, it will be a cos term. So Ey equal to c cos kappa x. So just like we did in the previous classes, we can find this kappa, gamma, all these things by using the transcendental equations. Kappa h by 2 for minus h by 2 less than equal to x less than equal to h over 2. And then the third region, that is below minus h by 2, for x less than minus h by 2. For those regions, we will have against the constant times the radiating part, e power gamma x plus h by 2. Okay, so this x plus h by 2 will anyways be negative, so we don't need to put a minus sign here. It will be a radiating mode. So the next step will be to find uh, kappa, gamma, beta. So these things we have done in the previous classes, right? So we just apply the boundary conditions of the electric field and the derivative of the electric field being continuous. Then we'll get some transcendental equation, and from that we plot the LHS and RHS and find the values of kappa. From kappa we can get gamma and beta. So these all we know, so we skip it for the time being. So say we already know the gamma value, kappa value, say we know the values and the beta values. So now next thing is to introduce the perturbation. So how do we go ahead and introduce the perturbation? So perturbation is along the x, that will be nothing but the change in the epsilon times electric field, right? So in the initial part of the waveguide, we have assumed that we only have the forward propagating wave. So at before x equal z equal to minus a, we only have the forward propagating wave. So this electric field will be nothing but the field for the forward propagating wave. So let me just write this down. So what will be the delta epsilon? It will be the permittivity of free space into, now what is the change in the refractive index? The refractive index should have been n1, but it has become n2. So the change in refractive index, I should write it as n2 square minus n1 square. So if you remember, the epsilon is nothing but epsilon naught times epsilon r, and this epsilon r is nothing but it is nothing but n square. So that is what we are using here. So the change in delta epsilon will be n2 square minus n1 square. So this is n2, this is n1. So it should have been n1, it has become n2. So that is the change. So next thing is to write the electric field. So the electric field will be, so as we said, it should be only the forward propagating field. So half a plus, then the mode field amplitude of the forward propagating field, that is this term, that I'll just write out for now as Ey as a function of x, because this direction is x, this direction is z, e power minus j beta z minus omega t plus complex conjugate term. So and we have to note that this thing is there only in this particular region. So I should write here, for 0.4 h less than x less than 0.5 h, because x equal to 0 is here, so this is zero point 0.5 h and this is minus zero point 0.5 h. So and then this is just h by 10, so h by 10 will be at zero point 0.4 h. And also for this z goes from minus a to plus a. For any other place the perturbation is 0. So yeah, so now we have written the term p part of x. So now we just need to substitute in the equation that we wrote, that we found in the previous page. So this was the equation, this is the coupled mode equation. So we need to find the backward propagating wave. For that we just write the p part term here, and the rest of the things we will substitute. So it will become right. So yeah, so now this is how my equation looks like. Now LHS is fine. We need to put my p part in the RHS part, so that will become minus j over minus j over 2 omega dou square over dou t square zero point 0.4 h 2.5 h epsilon naught into square minus n1 square. Now note that the p part term also has an ey of x, and there is an additional ey of x here, so then that will be a ey of x square. So then there will be a ey of x square, and then the rest of the terms, that is half a plus e power minus j beta z minus omega t plus complex conjugate dx. So of course the integral is in dx. So this becomes now let us substitute for ey of x. So ey of x in 0.4 between in this region that we will see is only the forward propagating. So ey of x will be this term. The mode term will be the propagating mode term, not the radiating mode term. So then we will have after substituting, so there is this minus j over 2 omega, then dou square by dou t square. So what is the t dependence here? T dependence is coming only from this particular term here. right? So the differential will be, so if we do double differentiation, so there will be omega square, j square. So j square, I'll write omega square this 2 here, um, or let this 2 be for now. So okay, I'll just take out the omega square. This time I'll write it separately again here. Uh, then epsilon naught and 2 square minus n1 square also can come out of the integral. Times, this time I will write entirely like that only, half a plus e power minus j beta c minus omega t plus cc. So this is after the differential is already done. Now only the integral part of is left. And integral is over dx. So only term that depends on dx is this term. So 0.4h to 0.5h. The square will be c square cos of kx by cos kh by 2 square dx, right? So further simplifying, j square is minus 1, this minus 1 gets cancelled, omega square, so I will have j omega epsilon naught n2 square minus n1 square upon 2 into this term as it is into the integral. Okay, so all these things I can write it as j times k times the forward propagating amplitude e power minus j oscillating term beta z minus omega t plus complex conjugate. So I took all these constants and the integral into the coupling constant. So this is called the coupling constant, K, coupling coefficient. And how do I define it? Well, coupling coefficient is omega epsilon naught n2 square minus n1 square upon, so since I've removed the half here also, I should include it here, so upon 4.4h into 0.5h c square cos kappa h upon kappa x upon cos kappa h by 2 square dx. So all this analysis is only for the perturbed region. So that is for, because in other regions there is no perturbation at all. So the p per term will be 0. So this is all for z between minus a to plus a. And this coupling coefficient is case specific. So in another case, any other case, any other example you have, you write it in terms of the complex term times kappa times the amplitude and the oscillating term of the mode, and then whatever is the kappa is the coupling coefficient of that mode. Okay, so what does this mean? So just to recap, the LHS side, So on the LHS we have dou A minus upon dou Z e power j beta Z plus omega t minus dou A plus upon dou Z e power j beta Z minus omega t plus the complex conjugate is equal to j coupling coefficient times a plus e power minus j beta Z minus omega t plus coupling sorry, complex conjugate. So this is the expression that we have. I think there is a minus here. So now if I just multiply by e power j beta Z on both the sides, so if I multiply by e power j beta Z minus omega t on LHS and RHS, then what will I get? So I'll get dou A minus upon dou Z e power 2j beta Z minus omega t plus omega t will get cancelled minus dou A plus by dou Z e power plus j beta Z minus omega t minus j, these two terms get cancelled, plus coupling plus complex conjugate is equal to j kappa A plus, again this term and this term will get cancelled, plus complex conjugate. So now for large z values, since this is an oscillating value, if I integrate over large z values, then this value will be very small. It will average out to 0. So what is left is, for integrating over large z, what will be left is minus dou A over dou Z is equal to jk A plus, and since I am integrating from z goes from minus a to plus a, if I integrate from z goes from minus a to plus a, what should I get? So I will get a plus of plus a minus a plus of minus a, right? And there will be a minus sign, so I will get a plus of minus a minus a plus of plus a is equal to sorry, I made a mistake. So we are not integrating from minus a to plus a. We have to integrate it from minus a to some z value. So we will see how my amplitude changes as a function of this z value. So if I increase the z value, how my so that's why I am keeping it as a z instead of a plus a. So obviously this z cannot go beyond a, because after that there is no perturbation anymore. So then then after integrating this, what we will get is a plus of z is equal to a plus of minus a times e power minus j kappa z. Right. So now this dozer you take it here, then integrate, then you will get this. Yeah. So a plus comes down here. So dou a plus by a will be log a, and dou z will be just z. And then after putting limits and after noting that a0 equal to a of minus a, because yeah, that is where we are starting from. So then you will get something like this. So the log term, I just made it into an exponential term. So that is that. Now, uh, if my amplitude is varying like this, so we have already gotten the amplitude variation of the forward propagating amplitude. So the forward propagating amplitude is nothing but the forward propagating amplitude at minus a with the additional phase term. So if this is my amplitude variation, um, my e of xz comma t will look like, let's set it as e. Electric field will be nothing but a plus z. So a plus z is nothing but now a plus of minus a by 2 e power minus j kappa z minus j kappa z plus beta z. So that will be beta plus kappa z plus complex 1j for minus a less than z less than. So similarly, I can also so what we did now is we assume that this term will go to 0, and we use this relation to get the relationship between the forward propagating amplitude and the coupling coefficient. So now we need to get a relationship between the backward propagating amplitude and the coupling coefficient. So from this relation we note that the change in the forward propagating amplitude is very small for small z value. So it is just a change in the phase. There is no change in the amplitude as such. So by noting that, we can just ignore this term and then equate these two terms now. So we will get, for the reflected wave, and so a minus at a is 0. So if this is my perturbed region, here the backward propagating is 0. So because we are not getting any reflections from this region. So here at this point the backward propagating will be 0. So yeah, and at this point it will be the max. So yeah, all the backward propagating wave is coming only from the perturbed region. So a minus of a is 0. By noting that and integrating from minus a to plus a on both sides, I'll get a minus of minus a is equal to j kappa a plus by beta sine of 2 beta a. And so this term I moved it here and then integrated it. So dou a by dou z will be a minus of minus a minus a plus of minus a minus of plus a, and then the integral of e power 2 theta is sine. So that's how we get the sine term. So the key takeaway from this is that we have found the reflected wave amplitude change with respect to the coupling coefficient kappa, and we have also found the forward propagating wave amplitude change with respect to the coupling coefficient kappa. So with respect to coupling coefficient, the forward propagated amplitude is only shifted by some phase, and the reflected wave it changes based on the thickness of the perturbation, or based on a. So I could have written this easily as minus z instead of integrating it from a to minus a. I could have a to some z value, I could have integrated it. So then in those cases this would have been z. So based on the z, based on the amount of perturbation, so since we are applying this boundary condition here, so we have to take it in this direction. So based on the amount of perturbation region, the amplitude of my reflected wave will change. So based on the thickness a or 2a of the perturbed region, the amplitude will vary sinusoidally. So the coupling to the backward wave is maximum when will it be maximum? When this 2 beta a is nothing but sine 90 is 1, right? So that should be equal to pi by 2 or 3 pi by 2 and so on. So odd multiples of pi by 2, or you can write it as some q plus half into pi, where q is an integer. So in terms of a, we get maximum reflection when q plus half pi by 2 beta, when a equal to q plus half pi by 2 beta. So that is what we have found out from all this analysis. So now what we did is, we just had a single mode waveguide. Just to recap, we had a single mode waveguide with one mode propagating in the forward direction, but there was some perturbation in this region. So because of that perturbation, we got an additional reflected wave, and the amplitude of the reflected wave changes sinusoidally with the length of the perturbation. And we found out how it varies and how the forward wave varies. This, I think I forgot to write the electric field term. Yeah. So now what will happen if instead of a single mode waveguide, I had a multi-mode waveguide? Say I have See, now I'm not worried about the backward reflections, but I'm just worried about, again, I have a perturbation. I had single mode, say A, propagating first. Because of the perturbation, now after the perturbation, I'm seeing two modes. Now they both are in the same direction only. But it is possible that some of the energy got coupled from mode A, which was, say, the fundamental mode, to the mode B, and again to mode A also. So now there are two modes instead of one. So how much is the coupling to mode B from mode A? How do I find that out? Again, we can approach this problem with a similar approach, perturbation theory approach. This is the second problem. This I'll mark as problem 1. Just to repeat the question. So now instead of a single mode waveguide, I have a multi-mode waveguide. So instead of just one mode propagating, I can have multiple mode propagating. Now I just excite one mode to the left, and this mode is propagating along the z direction. But there is a perturbation along the x direction that causes the mode to change its amplitude. The amplitude of the mode changes, and some of the energy gets coupled to an additional different mode, that is mode B. So how much is the coupling we have to find, and how to approach this problem. So again, here also, this is z equal to minus a, this is z equal to plus a, the height and all the other things remain the same. So let's do it. So first let us start with writing down the mode A, how it will look. A of x comma t comma z also, obviously, but okay. So that is equal to a by 2 ea of x e power minus j beta a z minus omega t plus the complex conjugate term. Eb of x comma z comma t is equal to, again, the amplitude b over 2, the mode profile of mode B, times the oscillating term beta b z minus omega t plus complex conjugate. So these are the two modes. So for z less than a, optical energy is in mode A. For z less than minus a. So if I want to write the couple, so what do I want to find now? I want to find how much energy got coupled into mode B. So for that I need to write the coupled mode equations for mode B. Again the same thing, dou B by dou Z. Now we are assuming that we are mode B is also forward propagating, so we only need the information for the forward propagating mode. However, for now let's write down both the terms just for e power minus j beta b z minus omega t plus dou b minus upon dou c e power j This is backward propagating beta uh, plus omega t plus the complex function. So it's possible for some reflected wave also. However, we don't want this beta b. We want the relation for beta plus with respect to the perturbation. It is equal to minus j over 2 omega dou square by dou t square integral minus infinity to plus infinity p pert eb of x dx. So now what is this perturbation? So this perturbation is nothing but this region, right? And predominantly which wave is present in this region? It's the mode A. So that is my perturbation. So let me first write down what is my perturbation. P pert is equal to epsilon naught, again n2 square minus n1 square, that is the refractive index change, times the electric field. Electric field is predominantly Ea of x comma t. So we assume that the Eb is not formed yet. So that is my perturbation, and this perturbation comma zeros. So this perturbation exists only in this region. So again, I'm not writing down the limits, but we have to understand that it is existing only in this particular region. So from z equal to minus a to plus a, and from height 0.4 h to 0.5 h. Okay. So now, uh, what will be the coupling coefficient? So just like previously, we can write down the LHS as j times some coupling coefficient times the okay, first let me write down the RHS. RHS is nothing but what is EA? EA is A by 2 E of x e power minus j beta a z minus omega t into what is EB? Into EB is b by 2 EB of x e power minus j beta b z minus omega. Complex conjugates I'm ignoring for now. Like we can keep track of them, but just for the ease, I'm just not writing those terms. Okay, so I actually made a mistake here. Uh, so this wait a minute. This this is supposed to be EB of x, so that is just the mode profile of mode B. So I wrote the entire mode equation. So we don't the electric field equation. We don't have to write the entire electric field equation. We just have to write the mode profile. Okay. So that's like it's like the overlap between the perturbation and the mode in the profile of the mode in the x direction. That is what matters. It doesn't matter. The amplitude of mode B doesn't matter. The phase of mode B doesn't matter. Only thing that matters is the mode profile. So that is what we have to write. Yeah. So clearing that up. Now we have this on the RHS. So this I can write it as J. After doing the double differential, I'll get the j square out, that will cancel and stuff. So this I can write it as j kappa a e power minus j beta a z minus omega t. Correct? So where my kappa is nothing but omega epsilon naught n2 square minus n1 square upon 4, this 2 and this 2, integral. So the perturbation is not from minus infinity to infinity. Actually, the perturbation is from point 4 h to 0.5 h. EA of x times EB of x dz. Sorry, dx. I got confused. So 0.4 and 0.5 h are along the x direction. So dx. So this is the region for the perturbation, and now that is my coupling coefficient, and my RHS looks like this by putting in for the coupling coefficient. So now my entire equation becomes, so on my LHS I had minus dou B plus upon dou Z e power minus j beta B Z minus omega t. Bear with me, I'll just write it down. Minus B minus upon dou Z e power j beta B Z plus omega t is equal to, what is the RHS that I just got? J kappa a e power minus j beta a z minus omega t. So if I just multiply throughout by e power j beta a z minus omega t, then RHS will become just j kappa a. LHS will become instead of multiplying by beta a, I'll multiply by beta b, so this term. So then this will become minus j beta a minus beta b z. So I'm multiplying throughout by e power j beta b z minus omega t. Okay, So this RHS becomes like this. LHS will become minus dou beta plus by dou z. So why I'm doing this? Because I want to find this beta plus variation with respect to kappa. So I'm just trying to simplify that part. Plus b minus by dou z e power 2j beta b z, and plus omega t minus omega t gets cancelled, so that will be 0. So that is the plan. So the plan is that now I have got this as an oscillating term, so then again I can call it as a small term, and then I will write minus dou beta dou b plus by dou z as equal to the RHS, and then I solve for the b plus, that is the forward propagating amplitude. So now I have, so this term is very small, small for integral. So if I take an integration over a large enough value of z, this will average out to be a small number. So now if I take an integral from z equal to minus a to plus a dou b plus by dou z minus of dou b plus by dou z is equal to j kappa a e power minus j beta a minus beta b z. These. So this will become negative of b plus of a minus b plus of minus a. Correct? So that will be j k a. A is always a plus. Okay, so we are assuming that a is going only in the positive direction. Let me just write down the value after the integration. So after integration, what will I have? So integration is on the z term, right? So then I should divide by minus j beta a minus beta b times e power minus j beta a minus beta b z equal to a minus e power j beta a minus beta b minus into minus a, there is again a. So now what do we observe? What is beta plus of minus a? What is b plus of minus a? Sorry. So this was the perturbation, right? This is minus a. So what is my b plus at this point? So if I'm assuming that only a is here, of course at minus a also there is only a present, and then slowly due to the perturbation we are starting to see some intensity transfer to b, right? So at minus a, b plus of minus a will be equal to 0. So now I have b plus of a equal to this minus cancels, j cancel, what is e power theta e power minus theta minus e power theta, or e power minus x minus e power. So this is nothing but like a sine term, right? So by that formula I can write it as a so this is divided by 2 multiplied by 2, so I can write it as minus 2j k a plus over beta a minus beta b. So you can look up, there is a formula like that. This divided by 2j is equal to a sine, so that is sine of beta a minus beta b times a. So this is how my my magnitude of the mode 2 will vary with A. So, and of course, it will also depend on the coupling coefficient. So, it will depend on the coupling coefficient K, and also on the length A. So, if I just plot the amplitude in the intensity of mode 2 as a function of A, or even you can say Z, but as my perturbation length increases, the magnitude of B square increases from 0 and varies sinusoidally. So what will be this point? If I call beta A minus beta B as delta beta, then this point is nothing but pi over delta beta, because uh, sine pi will be equal to 0. That's why. So this will be 2 pi over delta beta. Similarly, what will be this point? This is the point of maximum coupling. Maximum coupling to mode B from mode A will happen when my delta beta, or beta A minus beta B, that is equal to delta beta, is nothing but another way to say. So this point will be nothing but pi by 2 delta beta, right? Pi by 2 delta beta. So for maximum coupling, I can write delta beta is pi by 2a, and then I'm writing a q because it can be any integral multiple, odd integral multiple of pi by 2a. Here it will be 3 pi by 2 delta beta, like that only, 5 pi by 2 delta beta. So for all odd q, my delta beta should be equal to q pi by 2a for maximum coupling. So that is. So till now we were talking about non-degenerate mode coupling. So first non-degenerate mode coupling that we looked was for a single mode waveguide, where a mode in this direction is getting coupled to a mode propagating in reflected mode in the opposite direction. So this is called non-degenerate mode coupling, which is contra-directional. The second case that we saw was, it was a multi-mode waveguide, and so one mode A got coupled to another mode in the same direction. So this was co-directional, same direction. So, but in both the cases, it was still a non-degenerate mode coupling, because the beta of this is not identical to the beta of this. Similarly, beta of this is not identical to the beta of this. What happens if my beta values are identical? If beta is identical, then we move on to the regime of degenerate mode coupling. So let us look at this now. So the next topic is degenerate mode coupling. Degenerate mode coupling means beta are identical for both the modes. So when can this happen? So one typical example is the example of a directional coupler. So in a directional coupler, I have two waveguides that come close to each other, and that results in a perturbation. So the fact that the refractive index of the cladding is not uniform, so there is another waveguide in your cladding region, so that alters the dielectric profile of the cladding, and then that causes a perturbation. So let's see how the directional coupler looks like. So now we are seeing the cross section part. This is my N1, this is N2. So these are the two waveguides. Okay, so these are waveguides uh, in the refractive index N1, and the surrounding region has a refractive index N2. So above and below also there is N2. So this is the direction of propagation. This. So this is my Z direction, and the cross section is the XY direction. So in the XY plane, how it will look like? So in the XY plane, it will look something like this. Okay. So this distance is given to be A. The waveguide width is given to be 2b. Similarly, this is symmetric, so this distance is again A, this is again 2b. So how do we go about finding the coupling in this? So say I give power in one of the waveguides, say waveguide A. How much power will be transferred to the waveguide B? That is the question. So first let us start like we usually do by writing down what is the electric field profiled in mode A, the form of electric field in mode A, in waveguide A, and form of electric field in waveguide B. So my EA again depends on X, Y, Z and time in this case, because there is confinement both in X and Y direction. This will look something like, because there is confinement in both directions, I should write, so there will be a cos like this and a cos like this. So it will be somewhat of the form A cos kappa X, that is the X direction propagation constant, kappa XX, times cos kappa y, but since now it is not at y equal to 0, so the center of the waveguide lies at y equal to a minus b and plus a plus b. So if this is my a waveguide, then I will write at y equal to uh, y plus a plus b. So my y will be somewhere in the negative value. When I add a plus b, it will come to 0. So that's why I should write a plus here. You understand, right? So I can write it as cos kyy itself if this point was at 0, 0. But since it is at a negative displacement from 0, 0, I have to add an a plus b term to it. Right? And then, of course, it has to also propagate in the z direction. So I should write a e power minus j beta z. So for now, I am dropping down the time dependence just for simplifications. So there will obviously be also a minus I omega t term, but we are not writing it right now. Similarly, I will also have an EB of x comma y comma z to be b cos kxx into cos. So since these two are identical, so we can assume that the propagation constants are also identical. Ky y minus a plus b. Now, because this is at a positive A plus B displacement. E power minus j beta z. So these are my equations for the two waveguides. Now say that I send light in waveguide A. So if I'm sending a light mode in waveguide A, there is some evanescent field that will interact with waveguide B. So then that will perturb waveguide B. So if I'm looking at it from the perspective of waveguide B, how will the perturbation look like? So let me write that down. We send light in A, and we seeing the perturbation from point of view of B. So P pert. So what is the perturbation? So B was hoping that everywhere around the refractive index will be how much? The refractive index should be N2. But now it is seeing after some distance there is a refractive index of N1 after the distance of 2A. So that is the perturbation that it is seeing. So the perturbation will be epsilon naught times N1 square minus N2 square into what is the field right now? The field right now is we are sending light only in A, so we will have a field as EA of x comma y. So that is the perturbation. That is nothing but epsilon naught times n1 square minus n2 square. So this perturbation exists only in a particular area. So that also we should mention for y between so and so and x between so and so. But I'm not writing it right now. But that is understood, right? So the perturbation is existing only for certain values of x and y. Okay. So that will be equal to EA of x comma y is nothing but. So this is the profile, right? So the electric field will also have a time dependence. So let this be EA only. So this portion is the EA of x comma y that we are talking here. So the mode profile, that is what we are talking here. A by 2 is the amplitude minus JB. So this A is what will vary with Z. So as the Z increases, some amount of amplitude from the mode in A will start shifting to the mode in B. So the amplitude of the mode in A will start to reduce. So this variation of A is what we need to find, and the profile will stay the same. So EA of x comma y will be just x comma y. Right. So now we wrote the perturbation term. So now I need to put this perturbation term in the perturbation equation of B. Couple mode equation for B. Couple mode equation for B. Now this I have to integrate over both x and y. So I'll put two integrals. Again, like always, um, so here first of all I have ignored the backward wave, primarily because the backward wave component is not there in this case. So we are considering co-directional coupling, and uh, when the light is propagating in one waveguide, it can only couple in the same direction in the other waveguide. So we do not expect any backward wave. So the change in backward wave magnitude will also be zero. So we just ignore those terms. So we only have the B plus term here. So I am dropping the plus sign because we are only considering the plus sign, plus term. So the change in the B term will be proportional to the overlap between the electric field in the uh, B waveguide times the perturbation. So this RHS we can simplify further, again like last time. So again I'll have minus j by 2 omega dou square by dou t square of, so the t dependence will only come from the p per term, where this is the t dependence. So that we can write it down as j square omega square times the same thing again. So double integral epsilon naught n1 square minus n2 square eb of x comma y into the perturbation term, that is a by 2 ea of x comma y e power minus j and the integral is dx dy. So then finally I can write it as minus dou b by dou z e power minus j beta z minus omega t plus complex conjugate terms, leave it, is equal to j coupling coefficient a e power, just like last time we did same things, beta z minus omega t plus again complex conjugate terms. So right, so this coupling coefficient is everything except the terms mentioned here. So all the things you can just combine it together, the integrals, the overlap, the extra remaining coefficients, the refractive index difference, everything combined together is this coupling coefficient. So the point is that we get it in this form. So once we have it in this form, it means that the change in amplitude of the mode B is proportional to the amplitude of mode A and the coupling coefficient, and uh, yeah, so this is the relation between them. So by symmetry, the change in amplitude in waveguide A will be just the same, because these two waveguides are identical and there is no difference. So in case I had sent light in waveguide B, then the change in amplitude in waveguide A would be just the same as the change in amplitude in waveguide B here. So I can just write down by symmetry beta z minus omega t is equal to j k a, sorry, not a, b here, because now the amplitude is in B and we are shifting it to A, e power minus j beta z minus omega t, right? So this is my equation A, this is equation B. So from these two equations, what do we see? So I can simplify it further by just, if I just multiply by this part, then we have dou A by dou Z is equal to minus J K B. If I just cancel this part by these two parts out, this, so these are my two equations now. So we need to simultaneously solve for both these equations. So yeah, so now they look like pretty decent equations. All the complexity is taken care by the coupling coefficient here. So from this, if I just do a double differential, so if I differentiate LHS and RHS and substitute in the second equation, I'll get, so dou square A by dou Z square is equal to minus J K dou B by dou Z. So this dou B by dou Z is now minus 1 by JK into dou square A by dou Z square. So this will become dou B by dou Z is equal to minus 1 over J kappa coupling coefficient into dou square A by dou Z square is equal to minus J K A. So from these two, what do we get? We will get a double differential equation. Dou square A by dou Z square is equal to minus K square, J square is minus 1, so that minus 1 here, into A. So this is the equation that I have. Now I need to apply some initial conditions to solve the equation. So for applying initial conditions, again just to remind you, these were the two waveguides that we had. This is my waveguide A, this is my waveguide B. So at Z equal to 0, I am saying that all the light intensity is in A. So this is the Z axis. This starting is Z equal to 0, and as it propagates, Z keeps on increasing. So at Z equal to 0, A of 0 is equal to 1 and B of 0 is equal to 0. So the amplitudes are normalized, so I can write it like that. I hope that is fine. And then if with this initial condition and this equation, I can write down the solution of A of Z is nothing but cos, just by integrating it, cos K Z. So now that I know AZ, what is my B of Z? B is nothing but dou A by dou Z into minus 1 by minus JK. So simply, if I just do dou A by dou Z is equal to minus sine KZ into K, which implies my B of Z is nothing but minus J sine KZ. And the KK got cancelled. So yeah, from this relation. So now I have my B and A. So A is varying as a cos function and B is varying as a sine function. So the intensity, if I look at it, say if I plot the intensity, so intensity is nothing but mod B square in the waveguide B as a function of my coupling length A, or you can say as a function of Z also. Then what we see that it is first 0. So in the at Z equal to 0, we assume that the intensity in B is 0. Then it increases gradually, saturates to some value, comes down and keeps varying sinusoidally. So so this will be at z equal to pi by k. So this will be at pi by 2k. So you see, so the electric field intensity keeps switching between the two waveguides. So it will keep going back and forth between the two waveguides, and based on the length of the coupling region. So say this is my waveguide, this is the z axis now. Okay, so say I put my light inside this one waveguide here. It is propagating, and after some time it will be completely transferred into this waveguide. Then again after some time it will be completely transferred. So in the you can also choose how much transfer you require. So based on the z axis, so uh, based on the distance of interaction. So say my waveguide is like this. Okay, so here there is no interaction. So say I am putting my light in this arm. So here these two waveguides are far, so there is no interaction. Then I brought them closer, and then I gave them some certain length of interaction. So this is my coupling length. So based on this coupling length, it will determine how much light is transferred into this arm and how much light is transferred into the other arm. So this is called a directional coupler. And based on this analysis, you can see that we can find out. So if I want to completely power transfer to the cross arm, I can find out the length for doing that, which will be pi by 2k. K is the coupling coefficient. And if I want to do a 50-50, so say 3 dB coupling also, that is also possible. So like that, we design the directional couplers. So just for completeness, I'll write down for complete power transfer, we have z naught equal to pi over 2k plus q pi over k, where q is an integer. So all these things we just analyzed and found out analytical solutions. Now let us try to put in some numbers and see how much power is transferred, how much, yeah, what is the period of the power transfer and all those things. So let us start with an example. So this example I have taken it from Clifford. In fact, most of the analysis that we did in today's class, it's there in Clifford. Say my refractive index changes between 1.499 and 1.5. So the refractive index profile looks something like this. So since there are two waveguides, so in two different regions, the refractive index will be 1.5. Okay. This is my x-axis. This is x equal to 0 point. This is x equal to -2. So this everything is in microns. So -2 micron. This is -10 micron. +2. Sorry, this is not -10, this is -12. This is +12. So the width of the waveguide is 10 microns. Now they're telling us that their pumping intensity in waveguide B. Okay. And the intensity that they are pumping in waveguide B is evanescently coupling to waveguide A. So then what will be the length of coupling length and everything that we have to find out. So I'll just write down the steps. I'm sure you can do it in using Mathematica or some other mathematical tool. So step one will be to find the solution of the for the waveguide. So basically that would mean, uh, so we already know how to write the mode profiles. It will be C into exponential of minus gamma x in some region, then C into e power. So I'll do one thing. I'll give you the electric field amplitude, so you don't have to find beta and all other beta, gamma, and all those constants. So I directly write down the electric field solutions for the unperturbed case. So the perturbed case we need to do. For the unperturbed case, the beta is given to be 94227 centimeter inverse. All other coefficients have the regular values, 8.85 into 10 power minus 14 farad per centimeter. Omega is 2 pi into 300 into 10 power 12 second inverse. Uh, Mu naught, so this is the frequency that they have given. Mu naught is 4 pi into 10 power minus 9 Henry per centimeter. Right. So if this is beta, and for writing the solutions for the waveguide A, write it down first. A of x is equal to C e power minus 2840. So this is the gamma value, x minus 0.0012 in centimeters for x greater than 0.0012 centimeters. So in this case, this is the waveguide A. This is waveguide B. Then in the center region, there will be an oscillating term. So why am I writing 0007? Because the center of the waveguide. So if you just look here, so this is 2, this is 12, so center will be at 2 plus 5, that will be 7. So that's why we have this 0.0007 upon cos of 1942 into 0.0005. So this is the height, and this is kappa. Okay. Okay, everything is in centimeters. C power 2840 x minus 0.0002 for x greater than, sorry, x smaller than 0.0002 centimeter. Right. So now what is this C? This C we can find out by simply normalizing. So, or if you remember the orthonormality condition, the orthonormality condition was just that minus infinity to plus infinity ei of x into ej of x dx. should be equal to 2 omega mu 0 upon beta I delta ij. So I already know the beta values, omega values, mu 0 value. I'll just put EA square here on the LHS and integrate, and I'll easily find out the C value. So the C that we get is 433.56. So it's just a matter of evaluation. You can use any mathematical tool to find out C also. So now we have the solutions. Uh, we have the solution of our electric field in waveguide A. Similarly, I can also write for electric field in waveguide B, just the so this, instead of minus 0.0012, it will become plus 0.0012, like that. Some corrections will be there, but otherwise the shape and everything else of the mode will remain the same. So yeah, so this is the mode solutions. So next thing is to write down the perturbation. So what will be the perturbation? So P pert, so I'll write it down from the point of view of waveguide B. So we have the intensity in A, we'll write it down from the point of view of waveguide B. Okay, so P pert will be equal to, so now the intensity is in A, so EA of x times the times the amplitude, obviously, e power minus I beta z minus omega t, because we have to write the entire electric field into the change in refractive index. Change in refractive index is nothing but epsilon times n1 square minus n2 square. So this is for minus 0.0012 less than x less than minus 0.0002, and it will be 0 elsewhere. So we also have the perturbation, we have the electric field eigenmodes. So let us write down. So we can do like just like we did last time, we can write down the coupling equation. However, I am skipping a few steps here and directly writing down the coupling coefficient. So the coupling coefficient will be nothing but epsilon naught omega over 4 integration from minus 0.0012, again these same limits, to minus 0.0002 into n1 square minus n2 square, that is 1.5 square minus 1.499 square, into the electric field overlap between the B field and the A field. So this will be my coupling coefficient, and that you can evaluate. You will get some value. We can evaluate that because we know we know all the terms in EA of x, we know all the terms in EB of x, so we can find the integral, and epsilon naught omega values also we know, so you will get it in the form of some number. So the number will come out to be 3.6217 centimeter inverse, and then your amplitude A of z, just like we saw in the previous discussion. So we have done all this before. So if you just look here, so my A of z will come out to be cos kappa x, and B of z will come out to be minus j sine kx. So this kappa or k, whatever it is a coupling coefficient that we just found out. There was the equation for coupling coefficient. So we didn't explicitly write down. So this coupling coefficient was all the remaining terms in this equation. So basically epsilon naught n1 square minus n2 square, then j omega over 2, then this 2 also. So all these terms combine, and the integral, of course. Sorry. And this integral between EB and E. So all this term combined is my K. So this K I just evaluated it here to be this. So I just wrote the value, but yeah, we can evaluate it because we know all the terms. And then so my AZ will be nothing but A naught cos kx, sorry, kz. Similarly, Bz will be sine j sine Bz will be minus j sine kz. Okay. So similarly, just like we found out last time, we can also find out the uh, b square values, and then they will again we'll see that they will vary sinusoidally with z. Okay, that's it for today. So we saw how to basically uh, approach a couple mode theory problem, or how to understand perturbations, how they couple power between different modes, and what is the general way of solving for how much is the power coupled. So here also you can easily find out the power coupled by just doing a square. So it will be nothing but a naught square cos square kz. So yeah, so you will use the perturbation theory approach in all the problems that we saw, all the cases that we saw, and we saw that the overlap of the perturbation with the electric field amplitude in the waveguide determines how much is the coupling coefficient, and how much is the coupling coefficient determines how the power couples. So how fast or how slow the power couples. If kappa is faster, is larger, then I would have had faster sinusoidal variation. So yeah, so that is all we saw today. We will meet in the next class.